On behalf of Predict, Presidency University Statistics Society, I would like to welcome you all to the second talk of the educational talk series Light Up. Today we have with us Dr. Aritra Halder, an alumnus of Presidency University. He will be speaking on curvature processes, directional concavity in Gaussian random fields. As for a small introduction, Aritra studied in Presidency University from 2010 to 2014 and then did his PhD in statistics from the University of Connecticut. Currently, he is an assistant professor at Biocomplexity Institute under the University of Virginia. Once the talk is over, the audience can have their doubts and queries regarding the talk answered. Until then, I request all of you to keep your microphones muted. And now I request Aritra to take over. Thank you.
Thank you, Oshani, for such a nice and precise introduction, I must say. And it is a pleasure to be giving a talk in my old college, which is now a university, which has given me so much. And I've spent such nice years in this university with all of the lovely individuals that were there in the department, as well as some very friendly non-teaching staff. And I must say it has played a significant role in shaping who and whatever the batch of 2013 and 14 are as of this day. So without further delay, I want to start my talk today. So it is titled Curvature Processes with a subtitle of Directional Concavity in Gaussian Random Fields. This is a joint work with myself, Dr. Sudipto Banerjee, Dr. Deepak Kede, who's my thesis advisor. And so this is a short introduction for the authors involved. So in particular, what I would like to say is Dr. Sudipto Banerjee is actually also an alumnus of Presidency College's Department of Statistics, but he passed out 20 years before me. So so this has been a very nice collaboration, and this fortunately resulted in the second chapter of my thesis. So I would like to give a brief introduction regarding what this work is about. So this work is about spatial statistics. So what spatial statistics is the statistical uncertainty quantification of variance arising in the response from observations that are sampled across different locations. So this naturally introduces some dependence in these observations. So in layman terms, what this means is that observations that are located nearby behave similarly. So if you're living, let's say, near another individual who is also being observed for this response, the two responses, yours and that other individual's, would be very similar because you share the same locality. For instance, the number of times you visit the grocery store would be very similar for your neighbor, your neighbor's neighbor, and you. So the entire domain of spatial analysis builds models to essentially quantify this dependence across the response. So naturally, you can understand that the assumptions that you study for your in your model class, which essentially involves independence across observations, is violated here. So what do we do when such things happen? So we essentially build a model which we will come into much later, which actually accounts for that uncertainty, which actually quantifies this dependence and then still is able to assume independence across these observations. So they are conditionally independent, no longer just independent. So by me saying conditional, they of course mean conditional probability. But that is one part of spatial analysis. The other part of spatial analysis, as you can see, is the study of a surface. So what this produces when observations are recorded across this spatial domain, what this produces is actually a surface, which is observed in 2D in the last plot. So what this plot shows you is essentially the state of Connecticut, where I graduated from. So these are 8 counties. You can think of them as localities. These 8 counties have zip codes inside them. and these zip codes are essentially marked with dots in the first plot. And neighboring zip codes in the next plot are being connected by green lines. So if two zip codes are located nearby each other, then you put a straight line indicating that they are neighbors. So this produces a graph. That graph is shown in the second plot. The graph is very complex. So what the graph essentially shows you is this neighborhood information, which zip codes are neighbors of which other zip codes. Right? And finally, when a process is observed, when these zip codes or individuals living in these zip codes produce observations or are recorded with respect to some observation, then it produces a surface that is shown in the third plot. Now, understanding this surface is another part of spatial statistics. So by me saying surface, I mean a mathematical surface. So this has topological properties which you are very familiar with, and all of you who are interested or are undertaking math pass courses, I think so, have fairly good amount of understanding of what a gradient is for a surface, what is a Hessian for a surface, what is a second derivative for a surface. This is basically high school calculus. So utilizing all of these tools which we learn in high school and throughout our undergraduate statistics, we can essentially quantify some topological properties of this spatial surface through a modeling framework. So calculating gradients is very simple in a math course, but then to attach a concept of uncertainty, a concept of error to these gradients, and also to the second order gradients is quite difficult. And it becomes even more a complex problem when you think about it with respect to a surface. So this surface is essentially obtained by a finite number of points which are located inside of this spatial domain of reference. So what is the spatial domain of reference? For now, let us assume that the spatial domain of reference is the state of Connecticut, right? And the spatial domain of reference essentially restricts the domain in which the response for these individuals is being observed. So we will not go beyond the state of Connecticut to observe the same response. So once we have fixed all of this, we are left with a surface. Now, the main goal of this work is to essentially understand and quantify uncertainty within the geometric properties of a surface, like a gradient, like the second order gradient. So what the gradient here represents is essentially what is the rate of change in response. How rapidly is the response changing if you move from one location to the other. Remember that when I introduced spatial statistics, I said that this introduces some dependence in between observations that are nearby, that are located in the vicinity of each other, that are located nearby. So naturally, gradients occur when you go from one area to the other and the observation increases. And the rate of increase of the response is essentially being recorded by the gradient. Now, the rate of increase of gradient as to how fast is the response increasing will change when you move from one location to the other. So for instance, if you look at my mouse pointer, the gradients that are located here, where the response changes from something low to something very high very quickly, is very different from the gradient located here. So to quantify these things within a random surface, so mind you, all of these are random surfaces. So if I observe the same process at a different time point, it will be something totally different. Right? So there is a concept of uncertainty. These surfaces are not static. So there is some error associated with this. So the model that we hope to build, that spatial analysis already builds, essentially quantifies this uncertainty, attaches a concept of error to a surface like this. Right? So to that end, I digress by giving you some background regarding the math behind all of this, the mathematics behind all of this. So what a surface is being represented by this figure. So C, the value C is a curve. Essentially, it is a curve or a geometric construct within this surface. Now, the surface has a normal, which is perpendicular to the surface at all points and points outside and points in outward fashion. This is the thumb rule that you learn in your cross products and all of that, which is essentially in high school, class 11 and 12. And with respect to the normal, there is a local tangent plane at each point. So the tangent plane is created by these tangent vectors, which essentially if you take a linear combination of these tangent vectors, they span the tangent space. This you learn in your linear algebra in your undergraduate course. Now the violet dotted line that you see here is essentially slicing the surface along that direction, gives you a gradient which is along that curve, which is along a normal direction to the curve. So why is this curve so special here is because this curve actually bounds a peak. So the peak represents change, and we want to quantify change within the surface. Now, mind you, this surface here, as we are looking at it now, has no randomness. But then what we hope to do is build tools within this static surface framework and then attach a concept of uncertainty through these models that we have. Now, the rate of change, that is the gradient, is easy to find out because the gradient is not easy, it has already been researched. So that is the reason why it's easy. But what we aim to do here is essentially find out the second order property, that is how fast is the gradient increasing. So to understand that, what we need to do is, with respect to a surface, we need to actually see at what angle is the normal changing when you move along that pink dotted line with respect to the surface. So as you can see, it has been shown here. The normal going from, let's say, the lower location is shown by these small arrows, the normal at the curve, and then as you go further along that normal direction, how the normal changes. So as the normal changes, the angle in between the normal to the curve and the normal to the surface will also change. So that is the concept of curvature that we aim to quantify within these linear model frameworks. Right? So to give you some background, I will not go through all of this in too much detail, but then you need some background for it. So, and of course, with respect to the constraint of time that we have here. So the local geometry of a surface is determined essentially by fundamental forms, which are intrinsic to the surface. So each point in the plane, as you saw here, is essentially indexed by a local coordinate system, S1, which can be thought of as the x coordinate, S2, which is the y coordinate, and a function, which is essentially would transform into your response, which is indexed by these local coordinates. Now, the tangent vectors can be easily calculated. As you can see, if you just omit the third variable, this is the standard orthonormal basis for your Euclidean plane, the vectors 1, 0, and 0, 1. But then when we look at the tangent vector to the surface, they also come with the first order gradient when you're looking at the first coordinate, and the second order, the gradient with respect to the first coordinate when you're looking at the first normal vector, and when you're looking at the first tangent vector, I'm sorry, and when you're looking at the second tangent vector, you have your gradient with respect to the second coordinate, that is 0, 1, gradient with respect to the second coordinate of your response. Now, when you take a linear combination of these, what you get is the directional gradient space, which is essentially composed of a local coordinate and the directional derivative across the local coordinate. So this essentially is indicated by this violet dotted line, which is the direction of the normal and the gradient being projected along that direction, right? So why do we choose that direction is because that is the direction in which the peak lies. So that is the direction where maximum change is happening, and we aim to quantify that. Now, the first fundamental form is shown here with respect to a surface. As you can see, this is only composed of your first order gradients. So this is very essential in quantifying your arc lengths, your gradients within the surface at all different points. So the first fundamental form essentially quantifies all first order topological properties of a surface. Next, we come into what the normal is, because we want to find out and quantify the change in this normal as we move along the surface. So the normal with respect to this parameterization of a surface is given by this form. Right? So we are interested in how the normal changes as we move along the surface. So to illustrate that idea, it is just when we move from this point to this point, if you can see my mouse pointer. So you can see there's sufficient change in the normal, and the change in the normal would essentially involve change in the angle between the normal to the surface and the normal to the curve. Why is the curve important here? The curve is important for the main reason that the curve will essentially bound a region which encloses rapid change in the response. Right? Okay. So the second fundamental form under this parameterization essentially boils down to the Hessian, which is basically the matrix of second derivatives. So the matrix of second derivatives essentially then quantifies local change in the surface as to how fast the gradient is increasing, how sharply the gradient is increasing. Do we have a peak here? Do we have a trough here? By a peak, we mean peaks which project outward the surface as well as peak which go inward into the surface. Or is this a saddle point, which is basically flat in between two peaks, or there is no change in the response in that area? Right. So all of this is quantified by the second fundamental form with respect to a surface. Now, the normal curvature which we're interested in is something that is intrinsic to the surface. This is a property of the surface and not of the curve. The normal curvature essentially shows you how much the normal tips when you move in a unit direction, u, in the local coordinate system. So this essentially quantifies what I was trying to explain here. If I move a unit direction along the normal direction, how much does the normal change? That is a function of the second fundamental form. So, like I said, the second fundamental form quantifies local geometry of the surface. So essentially the normal curvature, being a function of that, essentially quantifies how much the surface curves at that particular point. U, as I said, is a unit vector, which is often referred to as a local coordinate or the local coordinate system. Now, in terms of spatial processes with respect to the surface, so all of what I said up till now is true and can be found in multiple textbooks, which range from high school calculus to differential geometry at the honors level. So now we come to what is a spatial, how do these concepts translate when you look at spatial processes. So we assume that Ys, which is the response, is a univariate weakly stationary random field. We assume additionally that it has zero mean. Without loss of generality, it has zero mean and finite second moment. So what I'm assuming is that the mean is zero and the variance exists. Now, how do we quantify in a statistical fashion the information that two nearby located individuals would essentially behave similarly? So that is being quantified using a covariance function, which you are very familiar with when you look at the multivariate normal. But this covariance function has special properties. So the special properties come from the fact that it is a function of locations. So if you're given two locations S and S dash, the covariance between the response of these two locations is a function of of how far these locations are located, of the distance in between these locations. So when you create a covariance matrix like this and generate a multivariate normal response from that, then you're automatically guaranteed that for nearby locations, the response that is observed will actually be very similar to each other. Now, K, this function, this covariance function K, is deemed to be a valid covariance if it is a positive definite function in RD. So we are talking about processes in general in the D-dimensional Euclidean space. Although the figure that I showed you is two-dimensional, you can think of, because it's easy to plot in two dimensions, you can think of this in a D-1 dimensional coordinate system with the last coordinate corresponding to the surface. Right? Because this is a surface in R3, so you have a coordinate system in the local coordinate system is in R2, that is the Euclidean plane, and the surface is in R3. Right? So in case of RD, the local coordinate system would be D-1, and the surface would be on the dth coordinate. Right? Okay. So there is something known as isotropy, which makes these covariance functions solely the function of the distance and nothing else. So that gives rise to some simplifications. So now, how do we even approach these concepts of gradient and curvature? So to do that, we need to first define what, just like the way you do in real analysis. What do you, to first understand gradient, you need the concept of continuity. Because if a function is continuous, then you can at least think of looking at differentiability. Right? So you say that a process, the stochastic process Ys on this spatial reference domain, is mean squared or L2 continuous if you take a sequence of points. It is the same definition. If you take a sequence of points and tend it to this location in a limiting sense, then the expectation, that is the squared difference, that's expectation would essentially go to zero. So that is the reason why we say this is mean square continuous, because this has an this has a concept of expectation attached to it, and this is the square of an absolute value of the difference. Right? So if you take a sequence of points, let's say S1 to Sn, that go to S0, which is this arbitrary location, then on an average, you would essentially approximate that location. So that is how you think about continuity for these spatial processes. Then we come to when do you say that a process is mean square differential? Then we rely on this our age-old Taylor series theorem, which essentially is used to have first order and second order expansions to give you the concept of first order gradient, which is denoted by nabla y at this arbitrary location, and the second order gradient, which is a Hessian, which we want to use to study the local geometry of the surface. And of course, they have these remainder constraints, which says that these remainders that you see from your Taylor series expansion actually goes to zero in a limiting sense. Now, to estimate these gradients and these curvature or these second order properties, you essentially need the concept of finite difference. This you study in your class 11 and 12 when you try and define what is f dash x, right? So when you look at f dash x, you say that let's increase the coordinate by a small amount and then take the difference and take a limit of that with respect to some scale. So that's exactly how we define this. The first order gradient is defined using the same concept. The second order gradient is defined using your second order finite difference. Now, the directional gradient and the directional curvature process, which we want to quantify, essentially is a product of these finite difference processes when evaluated at a limit. So you want h to go to zero, and then in a limiting sense, and then the process that it produces is actually your directional gradient process and a directional curvature process. So these are very simple concepts, which essentially you can encounter in your high school, in your math pass course, or even in statistics if you look at these kind of considerations. Right. So next we look at some theorems, which I'll not go into in too much detail. So we essentially look at what is the necessary condition for these processes to exist. These don't exist all the time, right? So of course, when you're looking at their existence, this would naturally boil down to how smooth your covariance function is. If you remember what the covariance function was, the covariance function essentially fixed how two responses which are located at different locations, which are close by, would essentially behave. So if you put constraints on how smooth this covariance function is, you essentially guarantee the existence of both the directional derivative and the curvature process in general. So this theorem essentially establishes that. But what is important here is what is shown in equation 3. With respect to a response, what it induces is a gradient and a second order gradient process. So vec h is actually half vectorization. Since the second order gradient is actually symmetric, because gradient with respect to 1 and 2 and the gradient with respect to 2 and 1, by 1 and 2 I mean x and y and x, is essentially the same. You can evaluate this under certain constraints when these would be the same. Of course, the constraints would be on the function y. So having both of these inside the process would essentially give you some level of redundancy. We want to get rid of that. So vec h is essentially the upper triangular matrix of your second order derivatives. So with respect to a process y, which we observe, so y here is observed. All of this is unobserved and induced. But all these differential processes essentially deal with the local geometry of the surface. Right? How fast is the response increasing when you go from one location to the other is being governed by the gradient, and at what rate is the gradient changing is being governed by the second order derivative, which is the Hessian or the vectorized Hessian here. Right? So the next theorem essentially quantifies that when you look at this process, you can essentially, assuming this process as a whole as a differential operator, you can essentially guarantee that this is a valid stochastic process. If if the actual process satisfies the conditions in theorem 1, which is essentially that it is stationary and its fourth moment exists. Right? So think of this as the strong law of large numbers. You know the weak law of large numbers, think of this as the strong law of large numbers. So if the fourth moment exists, things are really smooth. You would expect the first and the second derivative to jointly follow a valid stochastic process. That is what this theorem establishes. Then the next theorem is essentially goes down to these functions k, these covariance functions k, and what gives rise to these functions. So what gives rise to these functions is something which is seated deeply in Hegel theory. So these functions are essentially obtained as inverse Fourier transforms of spectral functions which are located like this. So when you have certain conditions on the spectral probability measure that gives rise to these covariance functions, you can essentially establish that the gradient and the curvature process would both exist. That is what this theorem essentially shows you, that we essentially establish the criteria on these spectral measures for the directional gradient and the directional curvature process to exist. Obviously, this is evident at this point that these don't exist every time. You require certain constraints to be placed on the original stochastic process that you observe. Right? So we provide some examples here, which are essentially commonly encountered examples. So one common choice of the kernel is the Gaussian kernel. Why do we call this the Gaussian kernel? Because this is exactly your univariate normal distributions kernel. But if you remove your probability constant, as well as if you set the variance appropriately, to get just the kernel for your univariate normal distribution. So this is the reason why this is known as the squared exponential or the Gaussian kernel. There's another kernel which gives rise to this, which comes from the T family of distributions, the T distribution with some new degrees of freedom, which is shown here, which gives rise to these covariance kernels that we deal with. So what constraints do we need on the degrees of freedom for it to exist? So essentially it boils down to when do the fourth moment exists, right? So if you evaluate those criteria for the Gaussian distribution, so as you can see, this is a very familiar form where your fourth central moment is actually 3 times sigma power 4, and sigma here is square root 2, of course. Right. So that's how all of this is evaluated. So like I said, we have these two kernels that we want to look at, under which we want to study the directional gradient and the curvature process. And the main reason why we look at these two kernels is because these are the only two kernels that exist in the statistical literature under which such gradients and curvature processes can be studied. Gradients don't require as much of a restriction, but of course, as you move to the next order of differentiability, you would require more smoothness, and that is where these two kernels only exist, where these stochastic processes can be studied. These are examples as to the matrix that was shown in this result, which looked very complicated, kind of boils down to something very simple with a lot of coordinates just going to zero, because so this coordinate essentially stands for the third central derivative, right? So that essentially evaluates to zero in the limit. So what you're left with is something very useful and very easy to employ is statistical combinations for these gradients, right? So we are still looking at the entire differential process as a whole. So this was your observed process, this is the gradient, and this is your second order gradient. Right? We have more examples, which, like we said, that we are looking at two different kernels. One is the squared exponential and one is the Merton. So this is for the squared exponential, what it boils down to. The first matrix is essentially in RD. The second is when D equals 2, which is actually your Euclidean space, which produces a surface in R3. Right? So that's the main reason why you have a smaller matrix as compared to this. Next we go into the first kind of Merton with a smoothness parameter that is much smaller, that's 3 by 2. Here, of course, things are not as differentiable as you would like it to be. Therefore, only the first gradient exists. So only the first order gradient exists. The second order does not exist. So for it to be like going to the second order, we would need the smoothness to increase. We would want more smoothed out observations. So as soon as you require that, then the parameter nu needs to be increased. And as soon as that happens, you get the full scale inference on the entire geometry of the surface. Right? So next, we look at Bayesian inference for these processes. So up until now, what we have shown is that without any assumption, without any distributional assumption, you can actually check the validity of such processes and when they exist and when they don't exist, and the criteria for these to exist. So next, we proceeded to prove a theorem which essentially inspects what are the consequences of assuming a Gaussian distribution on this y. So remember, y is a stochastic process. So you cannot just assume a Gaussian distribution on a process. So you have to assume that that process is actually a Gaussian process, whose realizations are actually Gaussian distributions, right? So it's being quantified like this. Right? So when you assume that on ys, this result essentially says that the entire differential operator that you saw here essentially follows another Gaussian process. And since everything in a Gaussian is very uh, well behaved, you have these properties which essentially say that if two processes are independent, their induced differential processes or their induced geometry is independent of each other. And essentially, you can add these two processes as well. So if you have two independent processes, you can essentially their geometry, the joint geometry is essentially adding them, and any subvector of this. These are all standard properties of the Gaussian distribution that we learn in your undergraduate course. So what's important here, what's the takeaway, is that this produces actually so finite realizations from this joint Gaussian process is actually a normal distribution, which is quantified like this. So as you can see, this first entry of the mean, I'm sorry, this first entry of the mean and this covariance is what the observed process is. All of the rest is essentially your local geometry. The first entity here is quantifying your gradient, the second one quantifying your curvature, which is the Hessian essentially. And all of this is being evaluated at a random location within this map that you have, within the spatial domain of reference, right? So Bayesian inference, as you know, that it requires some priors, it requires a likelihood, it requires posteriors. So what we show here in equation 6 is actually that these posteriors exist, right? And you can compute these posteriors by hand. And under the assumption of a Gaussian distributions, these posteriors boil down to something very, very simple. So using something known as composition sampling, you can essentially sample these gradients, sample these curvatures. So by me saying sampling, I'm also attaching this concept of randomness to these gradients and these curvatures. Because the surface is random, the gradients and the curvature are of course random. Right? So within this framework essentially produces a way to infer on these gradients and curvatures for random surfaces. Next, we come into this a theoretical application of what we created and proposed into studying rapid change, right? So if you remember in the first plot that I showed you, there was a curve C. And I said that the curve C was important because the curve C essentially allowed us to bound regions that enclose rapid change. So when we are trying to bound regions, we cannot, of course, infer on every point on the curve. That would be very unattractive and very cumbersome, because that would involve a lot of computation at all different points. No matter how fine you go, there is just no way of being completely accurate. So we essentially come up with probability measures which quantify the amount of change that is being enclosed by a curve. So with respect to the gradient, what we end up with is the value or the concept of an average gradient enclosed by a curve. So as you can see, the curve is essentially located on the surface. And this curve can be projected, of course, into R2, which is the local coordinate, to obtain the projection of this curve and the projection of the peak onto R2 to understand how much of the response, how much change in the response is this curve enclosing. So we are not only interested in inferring about the rate of change of the response, which is the gradient, but we are also interested in inferring about how fast the gradient changes as we move along this curve. So think about an ant which moves from one location to the other. How much would the ant rise and fall when it goes over that surface? Right? So that is the whole thing that we aim to infer on with respect to these random surfaces. But of course, when we are illustrating this, the surface here is constant or has no randomness. So what we end up doing is essentially, as you can understand, that when we move along a curve, we are essentially thinking of it in mathematical terms. You're actually integrating, right? So you're integrating what? You're integrating the response, right? Or you're integrating change in the response, right? So change in the response on an average when you move across the curve, right? So to do that, what we end up with are essentially line integrals. So we have to come up with a way of estimating random line integrals, right? So that is what is being proposed in this entire work. So first, what we did was to contribute a new stochastic process, which essentially quantifies local geometry other than gradient, which is the second order gradient. And next, we come up with a measure, a probability measure, with respect to that stochastic process, which allows you to quantify the average change in local geometry when you move along a curve within the surface, right? So this essentially deals with how you talk about a curve. So a curve can be looked at as, if you go back to the figure, I'll use the figure to like essentially explain the concept. You can think about a curve, this curve C, when projected onto the Euclidean plane, as being indexed by a set in the real line. As you change the value of t within this calligraphic t set, the curve is traced out. Think of this as the circle, the two-dimensional circle, x squared plus y squared is equal to 1, let's say, being indexed by uh, 1 sine theta, 1 cos theta, 1 times sine theta, comma 1 times cos theta, right? So as you change the value of theta within a certain interval, you get different sections of the circle, right? So t behaves exactly like that. So we think of a curve as a parametric curve. You change the value of t. If you look at different locations within that same set, you essentially can trace parts and segments of the curve, right? So why do we look at a curve like this? Because it makes the treatment of our integral much easier, right? So then we come up with Wormling measures for gradients, which you see again is a line integral, which involves the normal direction, which is the direction that we are interested in studying the change, the gradient, and the arc length as to how much are you traveling, right? So that is what the Wormling measure is essentially composed of. So by me saying Wormling, the main reason why I say Wormling here is because it was developed by an individual named Wormble, and that is the reason why this entire framework is essentially of gradient assessment or surface topology assessment is known as Wormling, right? So these probability measures that are used are known as Wormling measures, right? So this is the total Wormling measure with respect to the gradient. This is essentially the average Wormling measure. So all you see when you go from this to this is the main change is that this is average with respect by being average with respect to the arc length of the entire curve, right? And the arc length of the entire curve can be observed by just looking at the length of the set, right? Because you're traversing this set to obtain the curve, right? So what we contribute again is the Wormling measures for this new stochastic process that we have come up with, which involves the second fundamental form or the Hessian or what you would like to call it, and this we call it as the directional curvature, and the direction that we look at is the normal direction to the curve, right? And that is the reason why these line integrals just involve the normal direction and the second fundamental form or the direction or the curvature or the Hessian of the response surface. So we formulate similar total and average Wormling measures for this, and that completes the theoretical part of what we have proposed. Next, we look at the distribution theory. Like I said, we were assuming a Gaussian process on the actual response. So naturally, you would expect that these being functions of the gradient process and the curvature process being functions of the original process would also follow Gaussian distribution. And by me saying functions, if this goes back to, I think, slide where I introduced the directional curvature process. That's here. So these are actually linear functions of the your original process. So when you're assuming that these are normal distributions, you would expect any linear combination to also be a normal distribution, and that is the exact fact that we leverage to obtain inference for our Womling measures as well, right? So I'll go back to. So that's exactly what this yields. So the joint distribution of the two Womling measures is, so of course there is dependence. So if the gradient has to increase for us to be actually able to study the rate of increase in the gradients. So the same applies for decrease, right? So there is some dependence in between the rate at which the gradient is increasing and the rate at which the response is increasing. So that is the reason why we look at the joint distribution of both Womling measures. The first Womling measure essentially looks at the total gradient along the curve, and the second Womling measure looks at the total rate of change in gradient along the curve. Right? So there should be some dependence, and that is being specified again by this normal distribution, which arises from the dependence on the original process. Right? So this quantifies the posteriors and the way we need to sample. This is again the way we sample gradients. We would sample this in the same way, and we of course want to sample this with respect to the observed process. Right? Now, a curve is a theoretical construct. A curve cannot, no matter how fine you go, like I was saying, no matter how fine you go, you cannot really essentially get a good approximation of what a curve is, other than a mathematical representation. Like when you approximate a circle or any smooth curve in R2, what you essentially do is you end up drawing small line segments. So you are essentially obtaining a local linear approximation, but that range of locality can be decreased to a very small amount to obtain a good approximation. So the same concept is applied here. Right? So when we approximate a curve, we essentially look at different nodes inside that curve, and then we assume that the curve is a piecewise linear function that is essentially being specified by these line segments as you go along traversing the entire curve. Right? And what these line segments have is that the amount you need to go from one point to the other to reach the next point, and that is the length of the line segment, and the normal direction, because the normal direction is really important to us, because that is the direction where change is occurring. Right? So altogether, when you combine all these line segments, you essentially obtain an approximation of how much rate of change or how much rate of change in gradients does this curve enclose within the response. Right? So what this next theorem essentially, what we prove here is that to be able to accurately approximate this, number one, you can actually approximate a curve by doing this procedure, which is intuitive. And to be able to obtain a good approximation, you need to have a fine partition, which is again intuitive. The more number of points you have here, and the more closely they're located at each other, with respect to each other, you would obtain a much better understanding of how much change in response or how much change in gradients is this curve enclosing with respect to a surface. And that's exactly what this proves. And you say that the estimated Womling measure almost surely converges to the true Womling measure. Okay, so now we come to all of this, all of what we have talked about up until now essentially talks about gradients and rate of change in gradients and their application to boundary analysis, which essentially looks at the amount of response enclosed within a curve, right? But how do we actually fold all of these new concepts that we've introduced inside a modeling framework? Because a modeling framework is what is going to account for that uncertainty, what is going to give you an estimate of that uncertainty with respect to response. So think of this as your simple linear model that you have. So mu, the function mu as a function of the spatial location as some regression parameters, like I said when I introduced this, is actually your x transpose beta, right? But your x is a function of s, because these covariates are functions of locations. Like you and your neighbor, you have individual characteristics, but you also share the same zip code, right? So these individual characteristics are being recorded by x, right? And so you have a general modeling framework. Like, let's say, what is the gender of that individual, or where does that individual go for groceries, or how long does that individual travel to reach from their house to work, right? So all of these can be quantified in terms of covariates, which are built into this hierarchical modeling framework. Why is this called hierarchical? Because they're hierarchies, right? The first hierarchy is essentially your trend surface, which is the usual linear modeling framework. The next hierarchy is this correlated error, which is your ZS, right? So what ZS does is, what ZS incorporates is all of what we have talked about. It has this covariance function, which is a function of parameters, which actually accounts for this information that two nearby located individuals will behave similarly. Right? So this quantifies that concept, right? So all of the uncertainty quantification that we talked about in the first slide is happening here. And this again is your random uncorrelated error, which has this assumption of independence. This is not independent because you have, so the K is not a diagonal matrix. But epsilon S is actually your usual white noise, right? Normal 0 sigma square I. Right? So that is, so here not sigma square but tau square I, right? Because sigma square is actually the variance of the entire process. Okay. So what this gives rise to us is a set of process parameters that we're interested to infer on, and we are considering a Bayesian inference here, right? So in general, this can be extended to not only the normal framework, but you can study binomial responses, you can study zero inflated responses, you can look at Poisson responses, you can look at gamma responses, and any other responses which fall in general into the exponential family. Right? And when you're looking at gradients and curvature, that is the second order property or rate of change in gradients, you're essentially utilizing Z. So the distribution of Z stays constant. The distribution of the response changes, right? When you go from this modeling framework into the more general modeling framework. But Z still stays as a Gaussian process. And that is what allows us to infer on these gradients and curvatures using the same framework that we have explained before. Right? So this essentially shows you the same composition sampling scheme that we had outlined before. So you within this modeling framework, we use the same scheme, but we use the effect Z. The effect Z here, and we look at gradients and rates of change in gradients for Z, because Z is where all of this spatial dependence is being accounted for. All right. And then the Wormling measures as a next step. So when you have the gradients and the rates of change of gradients, you can of course formulate the Wormling measures and infer on them accordingly with respect to a curve of your choice. Right? Oh, I'm sorry. Okay. And so under the assumption of priors, so like I said, within a Bayesian inferential framework, you have priors and you have a likelihood that gives rise to a posterior. So here, in the first setup, where everything is normal and you have a Gaussian framework, that this is the likelihood. This product term is the likelihood, and all of what you see here is the prior. So as you know, by the fundamental concept of Bayesian inference, prior times the likelihood is proportional to the posterior. So this is actually the posterior in terms of the parameters that you saw in the previous, in this part. So theta, bold theta, is the whole set of parameters that we're interested to infer. This is what is the posterior for this bold theta. So we would actually use this posterior to create conditional distributions, full conditional distributions, which we will use to infer for each individual parameter, that is phi, sigma square, tau square, your regression coefficients, theta, right? Okay. So then next we went on to some synthetic experiments. I'll not go into too much detail. What I'll just briefly explain here is that what if, so we are of course operating within this hierarchical modeling framework, right? But what if the response comes from a random, because most of the real-time responses come from random processes. They don't need to follow this hierarchical structure. So what we aim to do by our synthetic experiments that we conducted was that we aim to see if gradients and curvatures for these random processes can be analyzed. So what we did was we simulated synthetic data, which was not from the model. So as you can see, these are sine cos functions, but the way that these sine cos functions are structured is that they will change according to your location. So S1 is your x coordinate, S2 is your y coordinate. So the first one, as you can see, the mixed gradient. So if you take gradient with respect to x and y, you will get a 0 because there is no dependence. The second one, if you take a gradient with respect to x and y, you will get some dependence. So just by changing this much, you can see the change in the spatial pattern that is produced is observed in these plots. Right? The advantage of having a framework like this is that your gradients and your second order gradients is actually observed, is available in closed form, or is observed, right? Because you can differentiate this function once and twice with respect to x, y, twice x, twice y, or xy, right? So del x and del 2 del x del y exists and can be computed in closed form, which is not the case for real-time responses. So that is the reason why this is synthetic. Right? So here we show that how accurately we captured that. So as you can see, the first row is your original closed form gradient. So this is the process that is, this is the synthetic process on which we fit the model on. This is the closed form gradient. This is the closed form gradient with respect to x-axis, closed form gradient with respect to y-axis. And the second row essentially shows you the estimation. So what you can see here is that we are able to capture that unobserved gradient, that we built all of this framework for, all of this complicated mathematical framework for, is actually proving useful in capturing the gradients. And next we look at the curvature. So as you can see, as you will know that when you vectorize or look at the upper triangular matrix of a 2x2 Hessian, you get 3 entries. So these are entries for those 3 plots. So this is del 2 del x2, this is del 2 del x del y. Like I said in the first pattern, del 2 del xy is basically 0. So that is the reason why you have a flat surface. And this is del 2 del y2, and you can see their estimation. So the significance, although you cannot see here, maybe if I can zoom in a bit, you can see, but then, so you can see that there is a color code to the points. So all points which are negative are being marked with a different color if they're found to be significant. All points which are positive are marked with a different color if they're found to be significant. So what happens when you look at the surface which has no information in terms of their mixed gradient, you get no significance. All points are white. So that is kind of addressing how reliable is this framework in detecting significant gradients, right? And when we talk about significance, we are looking at 95% confidence interval. So if 0 falls in that, then you say it's not significant. If 0 does not fall in the 95% confidence interval, you say it's significant. So essentially you're doing a hypothesis test for if the gradient is equal to 0. A two-sided hypothesis test, of course. So next we go into Wormling. So as you can see, we are interested in curves which track rapid change, right? So within this surface, within the first surface, any peak is a rapid change. So some things marked in red are outward projecting peaks, and things marked in blue are inward projecting peaks. So if you look at a contour that bounds that peak, that essentially bounds rapid change. So when applied to that, our framework should be able to say that this is a Wormling boundary, and that this has a significant Wormling measure, or this essentially encloses a surface within the response that actually tracks rapid change, right? So that is exactly how we formulated these curves. And then we choose a curve, which is this curve D, which lies on a flat surface. So there you should not be able, you should still look like find significant gradient, but not find significant second order gradient, because the gradient is increasing at a constant speed, like at a constant rate. So that's exactly what we find. Since this is a synthetic setup, things are very perfect in some sense, but that's something we hoped for. The other thing is essentially if we can capture the exact magnitude, because this is a synthetic surface, you have your gradients in closed form, like I said. So you should be able to compute what is the true value of the gradient along this curve. So we did the experiment just for that. And here is the result of this experiment. As you can see, this is the column on your left is the true, and the column on your right is the estimate. So they're very close, and all of their interval estimates contain these true values. So what this essentially establishes is that both for the gradient and the curvature, you're actually close to the true value, right? And for the curve that I said, curve D, there is a significant gradient that is located, like we expected, but there is no significant change of gradient that is located. So this is the only interval which contains 0, right? And which was expected by the way we put these curves in place for like over the surface. Okay, so we of course did the same kind of experiments for the next pattern as well, but then I'll not include all of that. it's there in the paper, and if you look at my thesis, but then this kind of explains the ethos of all our synthetic experiments. So next we applied this to some real data. So the first real data looks at the Boston housing data set. This is a very classical data set. You'll find this almost everywhere online. This is used to benchmark a number of algorithms. Since the contribution that we make is very fundamental in some sense to the study of surfaces, we wanted to apply this to classical data sets. So the first one we start with is the Boston housing data. As you can see that this is the histogram of, so what the Boston housing data deals with is it has median house prices of houses located across the surface. And these are located, of course, you have the latitudes and the longitudes of their location. And so the histogram, the plot on your left is the histogram of these median house prices. And the plot on your right is the spatial distribution. As you can see, houses located nearby have similar prices. Right? This is what we have been trying to get to. But then there is something very interesting happening. There is one zone which is to your left is completely red, and there is the other zone which is completely blue. So this indicates rapid change as you go from, let's say, left to right. So house prices decrease rapidly across these areas when you go from left to right across this entire spatial domain of reference. And we want to capture that. So we want to capture zones within this reference domain, which essentially house or enclose areas of rapid change. Right. So when located, these curves would actually cross certain zip codes or certain congressional districts, or in our case, it would be, let's say, the curve would go through South 24 Parganas. Right? So areas of South 24 Parganas which enclose rapid change in the housing market would essentially be located. So that's the goal of this. So this is just happening in Boston, right? So zip codes or census tracts or census districts which are enclosed by these curves essentially compose or jointly create a group of localities which house rapid change in the housing market, right? And this is all obtained through this Wormling boundary framework because the curve passes through these locations, right? So that's exactly, so the first thing what we do is essentially fit the model. So these are your estimates for your theta. So this is done using your hierarchical Bayesian model that we outlined in the hierarchical model section, right? So they are accompanied by their interval estimates as well. And then we proceed to doing, of course, a precursor to this Wormling framework, as you have already understood, is estimating the gradients of both orders, first and second. So once we are able to do that, then essentially we are able to look at curves and evaluate whether these curves enclose rapidly changing response locations or not, right? So we choose the two obvious curves, right? So the curves 1 and 2, one encloses houses which are essentially priced much lower than houses within 2. So houses within 2 are priced much higher, and they fall in a separate group. And houses within 1 are priced much lower. And we exactly want to see what parts of this curve 1 that we essentially obtain, which is a contour essentially, or a level set to be more accurate in mathematical terms, is what parts of this contour, when evaluated under this modeling framework, produce significant gradients or significant curvature. So significant gradient would essentially just give you the idea of change, like how fast is it increasing. But significant curvature would say, is the rate of increase significant or not? Right? So this would characterize houses that fall within these zones enclosed by these curves. Right? So you see that most of the curve 2 and curve 1 enclose significant gradients, which is obvious because the house prices at this location are increasing when you go within any direction, right? And we are particularly interested in the normal direction to these curves. So these are enclosed peaks. But as you can see, not everything ends up to be significant. So if I zoom in, you can see the parts that are not significant are just flat lines. The parts that are significant are bold lines. Right? So not every part of the contour, as was expected here, is not significant under this model. So only the parts which are marked in bold essentially house significant gradients or significant change. And when we move to curvature, things are just located in that zone of rapid change, which is expected. So which is essentially housing how rapidly is the gradient increasing. So the maximum amount of change is being located in these zones marked in bold, which are here and sparsely located in the curve, right? So this prompted us to look at what happens if you change the curve and look at a different set of curves, right? Uh, so that's when we come up with curves 3, 4, 5, and 6, which are essentially subsets of your curves 1 and 2. Right? Then you see a lot more curvature happening, right? Gradients are still significant, but then you get an exact complete zone where houses that fall within this area are all significant in terms of how fast the gradient is increasing. And also this location where you observe that the rate of change in gradients is higher. Right? So combining these two plots, the first one that I showed in the previous slide, and this as well as this, you obtain a set of curves which exactly demarcate a zone of rapid change in response and rapid change in gradients. So these in general house or characterize change within the housing market. So locations within the spatial domain of reference, that is the entire space when evaluated on this under this modeling framework, produces curves which, through this Wombling analysis or this boundary analysis framework, which essentially give us how locations of houses or groups of locations of houses which can be characterized to reflect maximum change in housing prices when you move across this spatial domain of reference. Right? So this would not have been, we could not obtain this inference just by fitting the model. Right? So all our expectations, for instance, the way we expected that this entire everything that falls on this contour should be in some sense significant, but that was not so. Right? So the accuracy, the concept of significance, and the concept of rapid change is all subject to this boundary analysis framework, which yields only segments and parts which are actually significant, which actually reflect rapid change that is significantly higher or lower with respect to the entire variation in the surface. Right? So all of the Wombling measures and their values are housed here, and you can see which ones are significant are not marked in bold. The ones which are not significant, that is include 0 in their interval estimates, are marked in bold. Right? So this is the same inference that I talked about with respect to these plots. Next, we look at another set of data, right? So this is the Meuse River data. So in this case, what we did was that we created our Wombling boundaries. These didn't exist. These curves don't exist in reality. We created these curves, and then we wanted to see if these curves actually house significant gradients or significant rates of change of gradients. But sometimes these boundaries are naturally occurring. So this particular data set looks at the Meuse River, right? So the Meuse River is a river in Europe, and what happens to this river is that when there's a lot of rain, it floods, and when it floods, there are industries which discharge their industrial waste inside the river. This river also floods the floodplain. Now, the floodplain is used for multiple reasons. It's used for agriculture. A lot of people grow crops here, so there's a heavy like agricultural industry here, and also there are individuals living nearby who grow local crops, and their local household animals graze along these floodplains. Cows eat grass in the floodplains, as simple as that, right? Because the grass is growing in a more fertile soil and it's tasty. So this looks at heavy metal concentrations along the path of this Meuse River after it has flooded. Because these heavy metal concentrations, or higher concentration of zinc or cadmium or lead inside of your vegetables, is harmful for your health in long term. So this is essentially a public health study as well as a hydrology study, right? So how do rivers behave, and how does the river affect agriculture, floodplains, the behavior of floodplains, soil treatment along along the soil concept, along the soil that's located near the river, right? So this essentially shows you, these spatial plots essentially show you concentrations of these heavy metals across the river Meuse when you look at the Meuse floodplain. Right? So what we do is that we independently fit Gaussian processes. We independently fit the models, the hierarchical models that we outlined, on each heavy metal, and that gives you this modeling estimate. Right? So here we actually have covariates. In the Boston housing data, we did not have covariates. So as you can see, we only had an intercept. here we actually have covariates. So these covariates are your regression coefficients. And as you see, distance is a spatially indexed variable. So this dist is actually how far is the point located from the river. Since we already have a random effect which is accounting for this uncertainty, this is no longer significant because all of that uncertainty is now being taken care of by the random effect. So the assumption of independence in your white noise is actually this white noise variance tau square is actually functioning only on the response because this is conditionally independent. Right? So this is no longer significant. This F frequency is essentially the flooding frequency. How frequently does the river flood? So you see, flooding gives rise to increase or decrease in heavy metal concentration is understood by significance. So flooding increases, flooding produces significant concentration in all heavy metals. So the flooding frequency too produces significant concentrations in all heavy metals, and that is the main reason why you see no bold here. So everything marked in bold contains the value 0, and everything that's marked, so that means the interval contains the value 0. So it's not significant. Everything not marked is significant. Right? So elevation is significant. Flooding frequency is significant. The lime content inside the soil is sometimes significant, but the soil in itself, as to soil properties, of course, don't matter because we're looking at the effect of these heavy metals with respect to the river flooding. Right? So again, for each of these models that we fit, we end up with the concept of significant effects. As you can see, significant effects are shown in the first plot. So these plots are essentially indexed by the first row is essentially cadmium, the second row is copper, third row is lead, and fourth row is zinc. Right? So the first row is cadmium. All right. So when you look at cadmium, the first plot essentially shows you the Meuse River in black, and significant spatial effects that were located are marked with either positive significance or negative significance. Right? And significant gradients are shown in the next plot. Significant curvature is shown in this plot. Right? So altogether, you can see that there are regions where the gradient is not significantly increasing, but the rate at which the gradients are increasing, right, are significant, of course. And when considered together, you can see that there are common zones where you have gradients increasing and the rate of change is also significant. And in particular, what you see is this northern part, where you see maximum concentration and the rate of increase as you move further away from the river of cadmium concentration. So all vegetation or all agricultural industry that is located here, you would expect significant cadmium concentrations in these locations, but not so much in the south. The same thing happens for the next thing, which is copper, but then the effect is very restricted. The gradients are still significant, but you don't see too much rate of increase in gradients. So it's increasing constantly. So there is heterogeneity. So this heterogeneity is being captured by this boundary analysis framework that we have outlined. So if we had stopped just at the gradient, we would have no idea regarding are the gradients actually increasing. If the gradients are increasing, it's cause for concern. If the gradients are not increasing, then you understand that this is happening at a constant pace. And so your action towards handling how to control heavy metals across this region or heavy metal concentration across this region by placing, let's say, flood banks, which kind of restrict the river within a certain area, would be very different. The way you place flood banks would be very, very different as opposed to if you didn't have this information of the rate of increase. Right? So the next one is again lead. So you see the least amount of effect in lead, and again zinc. So all of these behave in a very correlated way. So the gradients in zinc are very different than the gradients in cadmium, but they're located in very similar places. So in general, this northern part is very heavily affected. This one part in the north and this one part in the south. Right? So as you can see, in most of these cases, the rate of increase is also significant here, as well as the gradients. So this kind of summarizes the Wurmling measures. And as you can see, only the significant ones are shown. The ones that are not significant, lead, the main reason why we saw the plots for lead were so sparse that they were there was no significant gradient or significant curvature located, and that is the main reason why a lot of it is not seen. So the maximum uh, concentration and the maximum heterogeneity in change was located for cadmium and zinc, because you had these longer lines, these bigger contiguous zones of significance in just zinc and cadmium. That's the first row and the last row of plots, right? And that is the reason why you see a lot of this is as a lot of the Womling measures turn out to be significant. Right. So concluding this, this essentially produces a complete inferential framework for performing boundary analysis over surfaces in R3. The introduction of this new curvature process and its associated inferential framework allows us to further characterize directional gradients based on the rates of change. So as you saw in both the applications, that there is sufficient heterogeneity in the way gradients behave. Gradients are not increasing in all locations like along the curve. So identifying these locations where they're heavily increasing would kind of allow the investigator to put in place like like any mitigation like effort this investigator is interested in at those places first, because those places are rapidly deteriorating. Right? So, for instance, in the case of the floodplain, you would want to look at those areas which house significant rates of change first, and then look at areas which house significant, non-significant rates of change, and then go to the gradient. So, look along the gradient path, but then address the first part which has significant rates of increase in gradients, because that is where you see the maximum change. Now, curvature for surfaces is a very central concept in the theory of differential geometry. So any differential geometry book you look at, you would find the study of curvature, the understanding of fundamental forms, and how they talk about these things in connection to the geometry of the surface. So it is mathematically natural to have frameworks, statistical frameworks quantifying both of these things for these spatial surfaces, for these random surfaces. Right? And attempts to produce such a unified framework can be dated back to at least 1984. For some reason, the reference didn't pop up here. But then, yeah. And from a statistical inference standpoint, the assumption of a Gaussian process, as you saw, proves invaluable when formulating this joint differential operator, this observed process yielding gradients and second order gradients. Right? And of course, adopting a Bayesian hierarchical inferential framework allows for Gaussian calibration while characterizing all these different points within the spatial reference domain. Right? So this is all facilitated by this prior times likelihood being producing a proper posterior, which is then leveraged to characterize points, maximas, minimas, elliptic points, saddle points, troughs, peaks, and all of that. Right? Now, the application of this work, of course, is not limited to just real estate and hydrology. As you saw, this we are living in the generation of a pandemic, and of course, this can be and pandemics are of course very spatially indexed, right? So they have a underlying spatial dynamic that addresses their variation. You can also use these to understand that, and they have a lot of environmental applications as well. And so these are the only two like applications I showed. There are other applications in the paper when it comes out, which you can look at, and also you can look at my thesis. And of course, in induction of this novel curvature process into the folds of Bayesian Womling is a natural consequence, and this essentially produces a complete framework that not only allows us to study rates of change for these random surfaces, but also the rates of change in gradients. Right? And this is not just true for Gaussian processes, but these latent Gaussian processes, where you have response arising from Poisson, binomial, anything. Right? But this change in the spatial domain is structured. Right? As long as you have that, you can use these methods. Here are some of my references. And lastly, I would like to remember my time inside of Presidency College. So on behalf of the 2013 and 14 batch, I was actually supposed to graduate in 2013, but then I had lost a year, and that is the reason why I'm the last batch. I'm part of the last batch of Presidency College. I extend my gratitude to the wonderful professors we had, including, but not limited to, Professor Bishwajit Roy, Professor Shourab Dey, whom we had the honor of being in the class of. Actually, BR sir was the first person to like actually come and tell me that you should study more, look at probability more, and like devote some more time into probability. And of course, the faculty and the department as a whole. Right? And we had some wonderful and very friendly non-teaching staff, to mention them, Orunda and Shanada. I would, without you, I think we would not have survived a day in the department. So thank you for your time and all of the adjustment. So I'm really happy to be able to give a talk here. I hope you enjoyed it. So yes.
Thanks a lot, Aritrada, for taking out time from your busy schedule and giving us such a nice and interesting talk. Now, if any of you from the audience have any questions, I'd request you to go ahead and ask them.
I had not exactly a question, more of a mm, I don't know, request actually.
Okay,
To I mean, could you give us some more, suppose even hypothetical examples of how this inferential framework could be applied in some more real life situations?
sure. So hypothetical examples, by hypothetical examples, do you mean examples in other domains?
Yes, sure.
Sure. Okay. So in other domains, for instance, like let's think about. So the two domains I highlighted was the real estate domain, where you see variation in house prices when you move along a certain region, right? And the other one was when you're looking at these floodplains. But then there is this other. So this other area of application which talks about environment monitoring. Right? So this is another application that we have, but this is not included in this presentation, but housed in its supplementary materials, which essentially talks about monitoring changes in temperature as you move across a certain region. So temperature, as you can understand, is very spatially correlated, right? Because a lot of zones lying in the same, let's say, bands of latitudes and longitudes have similar temperature within a certain month. Right? So changes in temperature occur as you go along, as you traverse latitudes and longitudes. But are latitudes and longitudes just boundaries? Can you just look at, can we can we come up with a more finer boundary, which actually uh, studies change in temperature. Now, change in temperature, why is it important? So, a lot of change in temperature is attributed to the occurrence of tornadoes. Is attributed to the is attributed to the occurrence of torrential rain or torrential flood, right? So, monitoring temperature is a very important concept. So, being able to bound a region which houses rapid change in temperature becomes important in real time, because then you're more uh, accurately able to predict locations of floods, locations of tornadoes, and actually characterize zones that these zones are at a higher risk. So essentially what you're doing is coming up with a differential uh, understanding of the response. In this case, your response would be just temperature and how temperature changes. Right? So the occurrence of floods would be actually indexed in zones which suffer from temperatures which give rise to higher rainfall. So you can use these methods to essentially come up with those zones. Does that answer your question?
Yes, yeah, surely. I
Okay.
mean, thank you.
Yeah.
Let's wait for say another minute if anyone has any questions, or then we will move on. Okay, so on behalf of Predict, I would like to thank Oritroda for taking for many things, for taking the initiative of contacting us, for showing such enthusiasm, and also for staying up so late. I mean, in his time zone, for for this talk. For that, I am very thankful to him. We all got an insight into many advanced topics in statistics and mathematics, and I'm sure we will all look them up more to get an idea of what is happening in research right now. Thank you.
Sure. Thank you so much for being in close communication with me and adjusting the schedule so promptly to accommodate my inconveniences. And I look forward to many more talks like this. And as soon as we come up with anything new, I would love to come back and give more talks and meet all of you people. And once this pandemic is over, I look forward to actually being there in the college.